Hey, so this is another intro proofwriting / math structures video, and I haven't done one of these in a while, so the first two of them are going to be up here, and I'm going to just continue as if you have seen those two videos before. So I need to talk about what a proof is, because before this I gave logical operations, and I talked about set operations and just basics of stuff, and the whole point of this is to develop the idea of how do you argue things in mathematics? And well, in math, what we use are proofs. And so a mathematical proof is a logically valid and sound argument which asserts the truth of some mathematical claim, whether that be about a mathematical object or a number or what have you. I guess I said mathematical object first, and that sort of encompasses everything. But it's just trying to say more things about math stuff that we think about. So, the assertion of this truth is done with the help of different axioms or statements that we assume to be true, definitions that we've made, whether that be like what we're actually talking about or some other tertiary things that turn up later on in the argument, and also previously proven statements. So, the thing here is that there are so many rabbit holes that you could go down. You could go down the philosophy rabbit hole of like, what do you mean by true? Or what's the logical system that we're using? Or what's the model of logic, in other words, that we're using? And then what's our axiom system and all of that stuff. Essentially, I've kind of already said what those things are in the video on basics of sets. However, I haven't really explicitly laid out the set axioms, and I think I linked to this in the sets video, or the basics of sets video, but I'll put down below a more technical listing of the at least set axioms that I'm assuming. But for what will follow, I'm just assuming that you have some knowledge of arithmetic and geometry and stuff that you would learn in middle school to high school range for material. I'm not assuming calculus for this, aside from the myriad of rabbit holes that I am avoiding and either linking to the description in order to explain them in full. I would like to touch on two things that are pretty important to writing a proof, and that is the ideas of a proof being logically valid and a proof being logically sound. So in terms of validity in mathematics, it helps to look at the statements that we're proving. So in most cases, and in a majority of the cases that you encounter when you read mathematics, a lot of propositions or theorems or corollaries or lemmas are stated in this if-then format. And generally speaking, a lot of the statements that we're proving in a mathematical context can be reformulated as conditionals or as if-then statements. Now, an argument, which is just a collection of premises, P1 through Pn, and a conclusion C, is valid if, should we just assume that all of the premises are true, then we'll be able to conclude that the conclusion is true. So what this comes down to in logical notation is just that you and together all of your premises, and then you see if the conditional of all of those ANDed premises implying the conclusion is true. And so the other way of saying that you want to show that an argument is valid is just to say that this symbolic statement is a tautology, or is that it's true all the time. So if you're not convinced of the equivalence between assuming all the premises are true and then figuring out the conclusion is true and the symbolic statement being a tautology, it's a good thing to think about. It definitely pushes some of the truth table ideas from that intro logic thing that I did at the beginning of this little series of videos. So if you want to think more about that, you can, and I encourage you to, but I'm not going to spend a lot of time on that here because the goal is to get to what does a proof look like, right? And looking at different types of proofs and looking at different math structures or mathematical objects and the relations between them and proving things about them. The other thing that I needed to define is soundness. So soundness is kind of like the mathematical Schrodinger's cat, because there are whole fields of mathematics that are defined by taking a soundness assumption into account. And then you also have the question of like, what axioms are we using? Are we using choice, for instance? And that can cause some soundness issues in the arguments that come up in mathematics, but people don't usually think about it because within specific fields of mathematics, there's usually an agreed upon set of premises which are considered to be sound that are at the foundation. And that's usually what we have as axioms. But then continuing on, you can get into some weird stuff. So just to say it, even though we don't think about it that much in practice, an argument is sound if given an argument in the form of the premises being P1 through Pn and a conclusion of C, we have that all of the Pi's are true for every I, which I runs from 1 to n. And so going back to the whole mathematical Schrodinger's cat analogy, in number theory, for example, there's something called the Riemann hypothesis, which I do not want to spend time on right now because that is not the point of this video or the series of videos. But there's this thing called the Riemann hypothesis. We don't know if it's true or not, but there are whole areas of number theory where you prove theorems assuming the Riemann hypothesis is true and assuming the Riemann hypothesis is false. So if someone were to solve the Riemann hypothesis to determine whether or not it's true, then you would just collapse basically half of a field of math, which is a very weird thing to think about. So there do exist these instances where we forego soundness in mathematics to try to develop further so that when we figure out whether or not something is sound or not, we get like a litany of results. Anyway, that's a thing that's out there in the wild. I just wanted to say something about it because we usually don't talk about soundness in mathematics, but soundness is pretty important in the background. So anyway, moving on, I should probably show you like what a proof looks like. To start, I just want to look at some things that we're probably pretty familiar with if we've had just some middle school algebra or some high school algebra. Or just even just some general arithmetic. The first thing that I want to prove is going to be, for that reason, very basic. If you are someone who is well-versed in math or has a good background or is a very strong or has been a very strong math student throughout most of your life. And that is that the product of two odd integers is odd. I said earlier that most of these statements that we prove can be translated into if-then statements. I won't do this for the rest of the statements in this video, but for this particular statement, we can translate this into an if-then statement by saying that if a and b are integers and a and b are odd, then the product ab is also odd. To prove this, we go ahead and just let a and b be some integers that are, well, odd ones. And by definition of something being odd, it means that it's not even. So an odd number is just a multiple of 2 plus 1. So a can be expressed as 2n plus 1, and b can be expressed as 2m plus 1 for some integers n and m. When we go ahead and look at ab then, and we go ahead and multiply out the quantity 2n plus 1 times the quantity 2m plus 1, we end up getting 4nm plus 2n plus 2m plus 1. Factoring yields us 2 times 2nm plus n plus m, closed quantity, plus 1. Now, because this is a proof, and just to explain everything, right, since the integers are closed under addition and multiplication, which means if you take two integers and add them together, or take two integers and multiply them together, you get an integer out, we know that 2mn plus m is also an integer because 2, n, and m are all integers. And thus, because a times b is in the form of 2k plus 1 for some k an integer, which in this case that k is 2mn plus n plus m, we have that ab is an odd integer. There's a few things to point out here, and that the things that we did, or the things that we talked about here, were all generalities, right? At no point did I specify a particular number from the integers, or a particular odd number, or a particular pair of odd numbers. I always just worked generally with arbitrary things, and was still able to conclude that whatever product I took of those quote-unquote arbitrary things, I would get out a object with the desired property. So for this second example, I want to do something just a little bit more difficult, but is still within the realm of probably like background knowledge that you have from algebra or elsewhere in your mathematical career. And that is, I want to show that the square root of 2 is irrational. And so this might be pedantic, but what we're saying is that we want to show that the square root of 2 is not rational. That is, it cannot be written as a fraction reduced in lowest terms. That might seem straightforward, but generally speaking, in a lot of mathematical contexts, when you're asked to prove that something is not something else, or that you're looking at an object and you're trying to prove that it is not another thing, this can be very difficult. The way that we approach this is we sort of just flip the script on what we're doing, and we suppose, by way of contradiction, that the square root of 2 is actually rational. Now, when we do this, what we can say is that then there must be some natural number k such that the square root of 2 is equal to n over k for k the smallest, where n is just some integer. But I need to further suppose here that k does not equal 0. So this is not an issue if you are someone who believes the natural number starts at 1, and it is a problem if you're someone who believes that the natural numbers start at 0. Because you have the square root of 2 is equal to this fraction n over k, we can go ahead and multiply both sides by k. So k times the square root of 2 is equal to n, and well, n was an integer, so k times the square root of 2 is also an integer. The trick here is to think of something that might break what's going on. You can take a moment to do so if you would like to, so I'd recommend that you would pause here if you want to think about this a little bit more. So, if we go ahead and consider m is equal to k times the quantity, the square root of 2 minus 1, what ends up happening is we can go ahead and start observing properties about this m value that we wanted to consider. So the first thing to notice is that when we go ahead and multiply m out, we get m is equal to k squared root of 2 minus k. Since k squared root of 2 is an integer and k is an integer, we know that k times square root of 2 minus k is also an integer, because again, integers are closed under addition and subtraction. So you can add or subtract any two integers and get an integer out. Further, m is going to be a natural number, and it's going to be a natural number that is strictly greater than 0. And this is because the square root of 2 is greater than 1, and at the beginning of all of this, we suppose that k was a natural number. So k is also greater than 0. So we have k times the quantity square root of 2 minus 1 is going to be greater than 0, and we already said it was an integer, so integers that are greater than 0 are natural numbers. If we look at m times the square root of 2, when we go through and expand that out, we're going to get 2k minus k root 2. Now, k and 2 are integers, and the integers are closed under multiplication, and also k root 2 is an integer from earlier. So the difference between those two will also be an integer, because integers are closed under addition and subtraction. But now we've got an issue, because k was supposed to be the smallest positive integer, such that k times the square root of 2 was an integer. Now we have this m, which is less than k, which does the same thing from the third property. So from these four observations, we can go ahead and conclude that k was in fact not the smallest integer that could do this, which is a contradiction to what we assumed about k. Because we arrived at this contradiction, the thing that we supposed at the beginning of trying to form this argument must have been false. So we must have that the square root of 2 is not a rational number.